You are hunting for one name in a contact list. With a handful of names, any method feels instant. But picture 10 lakh names, and suddenly the method you choose is everything. The name you want might sit right at the top, or buried in the middle, or not be there at all. So there are really three honest questions to ask. In the luckiest situation, how little work can we get away with? That is the best case. In the unluckiest situation, how much work are we forced to do? That is the worst case. And on a typical day, how much work should we expect? That is the average case. And the language we use to answer all three is big O notation, a way to describe how the work grows as the input gets larger. Let's fix two symbols. N is the size of the input, the number of elements in an array, say, and T of n is the number of basic steps the algorithm takes on an input of that size. Big O doesn't chase the exact count of T of n. It cares about the growth pattern as n gets large. And to see that pattern clearly, we lean on to simplifications. First, we drop constant factors. If an algorithm takes 5n steps, the 5 is just a multiplier. Double the input, and you still double the work. So we write it as order n. Second, we keep only the dominant term. Take 3n squared plus 500n plus 9000. It looks intimidating, but when n is huge, the n squared term utterly dwarfs the others. The 500n and the 9000 fade into the noise, and even the leading 3 is just a constant. So the whole thing collapses to just order n squared. That is the entire spirit of Big O. Throw away the clutter and keep the term that decides how fast the cost climbs. Let's actually watch these growth classes race. On the flat axis is the input size n. Going up is the number of steps. Now let me draw each curve, slowest growing first. Order 1, constant time, is a flat line. The work never grows no matter how big n gets. Order log n barely lifts off the floor. Even for enormous n, it stays remarkably low. Order n rises in a straight line, steady, predictable, proportional to the input. Order n log n climbs a little faster than linear. This is the pace of the best sorts. Order n squared curves up sharply. Double the input and the work quadruples, and order 2 then explodes. It rockets off the top of the chart almost instantly. The danger zone. Feel that gap. Down low, order log n. Up top, order 2 to the n. For large inputs, the class of the curve matters far more than any constant sitting in front of it. Here's the good news. Most of the time you can read the complexity straight off the loop structure. No heavy counting needed. Let's do 3. A single loop that runs from 0 up to n does its work n times. One pass, n iterations. That is order n, linear. Nest a second loop inside the first, and for every one of the n outer steps, the inner loop runs a full n times. That is n times n. So the total work is n squared, order n squared, quadratic. Nesting loops multiplies their counts together. The third pattern is the sneaky one. Here I starts at n, and every pass halves it. So I marches down. N, then n over 2, then n over 4, all the way to 1. How many halvings until we reach 1? Set n over 2 to the k equal to 1. That means n equals 2 to the k. So k is log base 2 of n. The loop runs log n times, order log n. Our first real example. Linear search in an unsorted array. Walk from the front. Compare each element to the key and stop the moment you find a match, or when you run off the end. Best case. The key sits at the very first position. One comparison and we're done. Completely independent of n. That is order 1. Worst case. The key is missing, or it hides in the very last slot. Now we must inspect all n elements. That is, n comparisons. Order n. The average case is the interesting one. Assume the key is present, and every position from 1 to n is equally likely. If it's at position I, we make I comparisons. So we average I over all the positions. Now use the sum every one of us knows. 1 plus 2 up to n equals n times n plus 1 over 2. Substitute it in, the n on the bottom cancels one factor, and the average comes out to n plus 1 over 2. For large n, that behaves just like n over 2, which is still order n. So linear search lands here. Best order 1, average, and worst both order n. And a quick sanity check. For 100 elements, the average is 101 over 2, about 50, roughly half the array. Exactly what intuition expects. Now binary search. But this time the array is sorted. Check the middle element. If it matches, stop. If the key is smaller, throw away the right half. If larger, throw away the left. Each step halves what's left. Worst case, we keep halving until a single element remains and we still have to check it. The range shrinks. N, n over 2, n over 4, down to 1. Same argument as the halving loop. Set n over 2 to the k equal to 1, and k is log base 2 of n. So the worst case is order log n. And here is why that log matters so much. Take a million elements. 2 to the 20 is just over a million. So the worst case is only about 20 comparisons. 22. Search a million element array. The best case is order 1. The first middle guess is the key. The average, which tracks the average depth of a balanced search tree, is again order log n. So binary search runs best order 1, average, and worst order log n. Your turn. Look closely at this snippet. The inner loop runs to I, not to n. Pause the video. Work out its worst case time complexity, then come back. It's a classic trap. Here's the walkthrough. When I is 0, the inner loop does nothing. When I is 1, it runs once, then twice, and so on up to n minus 1. So the total work is the sum 0, 1, 2, all the way to n minus 1. That sum equals n times n minus 1 over 2, which is 1 half n squared minus 1 half n. The dominant term is n squared. So even though the inner loop is shorter, it's still order n squared. The tempting wrong answer was order n. Trap 1. Quoting the wrong case. Calling binary search order 1, because you remember its best case is misleading. Unless someone says otherwise, complexity means the worst case. Here, order log n. Trap 2. Faking the average. The average case is not simply the best and worst average together. It depends on the probabilities of the different inputs. You have to actually weight them. Trap 3. Forgetting the worst case. Some algorithms have a lovely average but an ugly worst case. Quicksort averages order n log n, yet degrades to order n squared. When guarantees matter, the worst case is what counts. And trap 4. Treating big O as a stopwatch. It deliberately hides constants and small terms. Two ordinal algorithms can differ wildly in real running time. Big O tells you how the cost scales, not the exact seconds. Let's lock it all in. Big O is an upper bound on how the work grows with n. After we drop constants and lower-order terms, always name the case. Best is the luckiest input. Worst is the unluckiest, and the one that gives real guarantees. And average is the expected cost under a stated distribution. Remember the two searches. Linear search. Best order 1, average, and worst order n. Binary search. Best order 1, average, and worst order log n. Vastly better as n grows, and to recurrence is worth memorizing. One recursive call on half the input gives order log n. Two calls on the halves plus linear combining gives order n log n, the heartbeat of merge sort. Master these, and Big O stops being mysterious.